This math talk introduces the various number systems that we discuss in grade 9 in Ontario. And it begins by discussing or introducing the first set of numbers we call the natural numbers. So they are the natural numbers. And you're quite familiar with these numbers. We would consider them to be the counting numbers. So if I had objects, say dots, like so, and I were to count them, I would say that this is 1, 2, 3, 4, 5. I would not count them as 1, 2, 3.8, 4.7, 5.99. So our natural numbers are clean, entire numbers without a trailing decimal. And the symbol that we use is a bold-faced N. And so when we write the set, it looks like this. The next set of numbers that we talk about are what are called the whole numbers. And they actually only contain one additional number on top of the natural numbers, and that's 0. And our notation for the whole numbers, probably no surprise, is an uppercase W. So like the natural numbers that begin with an N, uppercase N. The whole numbers begin with a W, uppercase W. And that set of numbers looks like this. We now talk about the set that is known as the integers. And this is just an expanded set of these clean, complete numbers that include negatives. So to this point, the counting numbers, or the natural numbers, were all positive. The whole numbers were non-negative, meaning they have the counting numbers plus 0. So the integers now include numbers like -3, -2, -1, -50, -1000. Once again, no trailing decimals, nice, clean values. I like to say what we would use to describe golf scores. You're at -3 or -2 or +5 or +6. Or temperatures, it's -20 out, -40 out, or it's +35. Those are integer values. Again, no extra decimals. And that set is denoted with an uppercase I, a bolded I. Now that's what we use in Ontario. You will also see this used, which is a bold-faced Z. We don't use that in Ontario, but that's used many, many places. So if you see I or a bold-faced Z, we're talking about the set of integers, and they look like this. What's worth noting about these sets is they can be described kind of all as integers. You could say the natural numbers are all the positive integers, and the whole numbers are all the non-negative integers. And the integers are just the integers. So you can see that those sets lie within each other, and I'll draw a diagram at the end to give you an idea of how they're related. Now, the next major set of numbers can't be listed the way we've listed these numbers, left to right without missing any. They're what we call the rational numbers. And these are all fractions. And they result in all repeating or terminating decimals. So for example, 2/3 is a fraction. 0.75 is a fraction written in decimal form. So these both fall into the category of rational numbers, as does negative 0.58 repeating 58585858. The symbol we give for the rational numbers, surprisingly, is not R. You feel like it would be an R. It's actually Q. We use the letter Q to represent these. And it's because when you divide two numbers, you get what is known as a quotient. That's a quotient. A quotient is produced when you divide two numbers. And so we call these Q because they are rationals or ratios of two numbers. And let me show you what that looks like in terms of a definition. So our rational numbers are described as the set of Q, where Q is A divided by B. Now our condition is that A comes from the integers, so we select A from the integers, we select B from the integers, and we put one condition on. B itself cannot be 0. So any fraction, any repeating decimal, any terminating decimal falls in the family or the number set called the rationals, or Q. Now you might think that once we've covered all the positives, all the negatives, all the decimals, repeating and terminating, we've covered all numbers. But that's not true. There's another set, and they're kind of an unusual set, I would say, because they fit the description of non-repeating, non-terminating decimals. And they have a special name. They're called the irrational numbers. And they're all numbers that don't repeat and don't terminate. Well, the question is, what kind of numbers don't repeat or don't terminate? Well, as it turns out, you can create one really easily. Let me give you an example. We could take, say, 0.25. 225, 2225, and so on. No question that has a pattern to it, but there's no repetition. It isn't 25252525. You are getting increasing numbers of 2's between the 5's. As it turns out, there are no two integers in that entire set of integers that can be divided that will produce that pattern. They're irrational. You can't form a ratio to produce that. They're irrational. Other famous numbers in this family include, well, you know this one, pi. That's 3.14159, and it goes on and on and on. There is no pattern to it. It does not terminate. It does not repeat. That number goes on forever, and that falls into the irrational category. Any square root, cube root, fourth root of a number that is not a perfect square or a perfect cube will produce a string of decimals that go on and on and on without repetition and without termination. All of these fall into the family of irrational numbers. Now, if we can't write them as a quotient, as we said for Q, if we can't write them as a quotient, we say they're a quotient not a quotient. And so that's our symbol for the irrationals. And the set looks like this. Q bar, we call it. And we can really only describe it in words. They're the non-repeating, non-terminating decimals. Now you're probably saying to yourself, that must cover it. Well, in a lot of respects, we have covered all of our numbers. They are really the combination of the rationals with the irrationals. If you consider every number and say it either repeats or terminates, or it doesn't repeat or it doesn't terminate, then you've pretty much covered everything. And that's a special set of numbers. When we take all that is in Q and combine it, and our symbol for combining is this, which is called a union symbol. If we combine it with Q bar, we get all numbers that we need to describe the real world, and those have a fancy name. They are called the real numbers. And they are a very, very important set of numbers that we will use going forward in mathematics, the real numbers. And so their set looks like this. Now, if you want to get a visual or a picture of what this whole thing looks like and how the sets are related, have a look at this. If you look at the white box, that represents all the real numbers. So these are the real numbers right here. Everything in these two sections of this box. And it works like this. I think of those nesting toy dolls that you get where the small doll fits inside the next doll, fits inside the next doll. Well, this is how the sets work. You have the natural numbers entirely contained within the whole numbers. With this ring around the outside, this ring containing only the number 0. That's the only whole number that doesn't belong in the natural numbers. Then all of those whole numbers and the natural numbers are within the ring that we call the integers. And so the only thing that's in this donut around the whole numbers are the negative integers. So just refreshing here, we've got the natural numbers, which are the 1, 2, 3. In this ring, we've just got the 0. In this ring, we've got -1, -2, -3, and so on. All sets are infinite. They go on forever. But there are numbers that are in some sets but not in others. All of these numbers fit inside Q. Remembering that Q itself has all of the decimals that repeat or terminate. Now you might say to yourself, well, 3, why is 3 in the set of Q? Well, if you thought about it, 3 could be represented as 6 divided by 2. Or 30 divided by 10. That would be a ratio of 2 integers. It just happens to work out that there are no numbers after the decimal place. So all of these numbers in N, W, and I can be written in fraction form and therefore belong to the set of Q. Now to the right, we have a completely separate set of numbers, and these are the non-repeating, non-terminating decimals. And I give you some examples. Root 2, 3 times pi, 0.454454445, and so on. These cannot be produced by dividing 2 integers. So these are the family that we call Q bar, or the irrationals, not quotients. If you put every member of Q together with every member of Q bar, you create what are called the real numbers. And those are what we study in mathematics going forward.